Finally, after 3, 4 or more videos on the Euler sum and the necessary tools that belong to Euler sum, we are finally dealing with a problem where we have to find the value of a sum, basically value of a Euler sum. Yes, and this is basically sum from k equals to 1 to infinity, kth harmonic number of order 3 by k square. And we know the sum is given here, 11 Riemann zeta of 5 by 2 minus 2 times zeta of 2 zeta of 3. But how do we solve this sum? Yeah, that's a good question. Okay, so now let's go for solving this problem. To solve such problems, we basically need the integral representation of the Euler sum for this special case r equals to 1, which we just derived in the previous video, which I will link over here and in the comment section as well. So we know that sum from k equals to 1 to infinity of hk of order p by k to the power q. We know that this sum is actually equal to Riemann zeta of p, Riemann zeta of q, and then plus minus 1 to the power p by p minus 1 factorial integral from 0 to 1 and then li q of x and ln x to the power p minus 1 by 1 minus x dx. So this is the major formula that is going to help us to solve this problem. Yeah, so we can just substitute 3 and 2 over here and then 3 and 2 and then solve this integral. But notice that if we substitute over here 3 over here, we get ln square x. Yeah, and there's a way I can simplify this. Yeah, basically from the power of 2 ln x to the power 2, I can make ln x to the power 1. The way is basically there's a formula for symmetric Euler sums. Yeah, we have a formula that sum from k equals to 1 to infinity of hk to the order 3 by k square plus sum from k equals to 1 to infinity hk to the order 2 by k cube. Sorry, by k cube. Yeah. Now we have a formula for this sum. Basically, if these were p and q and p, then the formula was basically zeta p, zeta q plus zeta of p plus q. I have also derived this in my previous video, which I will basically link over here in the comment section. Using this formula, we know that this sum is actually zeta of 3, zeta of 2 plus zeta of 5. Yes. Now since we know their sum, if we want to find this out, it's like sufficient if we just find the other expression. Yeah, because after that we can just subtract the other expression from this their sum and then we get this expression. And if we take this expression for the integral and to solve using integral, here since its p is 2, it will just have ln x to the power 1. So the integral will be simpler, so we first try to find this other sum and then using the symmetric Euler sum formula we will get our required expression. Yes, does that make sense? Yes, it does. Now let's proceed to finding this expression. Sum from k equals to 1 to infinity hk to the order of 2 by k cube. So what will we do? We will basically use the integral expression, which was Riemann zeta of p, Riemann zeta of q. Basically p and q are the expression over here and here, and plus minus 1 to the power p by p minus 1 factorial integral from 0 to 1 liq of x ln of x to the power p minus 1 by 1 minus x dx. Okay, now our task is to solve this. Now let's substitute p and q. P is 2 and q is 3. Yeah, so this is Riemann zeta of 2, Riemann zeta of 3 plus minus 1 squared by 1 factorial integral from 0 to 1, and then li3 x ln x to the power 2 minus 1 is just ln of x by 1 minus x dx. Yes. So now this sum will basically be Riemann zeta of 2, Riemann zeta of 3, and plus integral from 0 to 1 li3 of x ln of x by 1 minus x dx. Now I will basically use the integration by parts. Yeah, in integration by parts also I will take li3 of x as u and this other expression as b. But before we go to integration by parts, let me show you the integral of the other expression. Yeah, let me show it over here. The expression is ln x by 1 minus x dx. Okay, the indefinite integral of ln x by ln of x by 1 minus x dx. Let me show you this. First of all, we make a u substitution, that is we make y equals to 1 minus x. After that we get ln of 1 minus y by y, and now minus dx is dy, so this is minus dy. Now we know that integral of minus ln 1 minus y by y dy, this is just li2 of y. We all know that. Yes. So using this indefinite, this is li2 of y, but initial integral was in terms of x, so again we have to take it in terms of x, and that gives us li2 of 1 minus x. So the indefinite integral of this expression is basically li2 of 1 minus x. Yeah. Yes. So now this was a sort per person. This was a sorter person. Just needed. Okay. Now let's write the reading. Riemann zeta of 2, Riemann zeta of 3, plus integral from 0 to 1. Yeah. And then we know that if you use integration by parts, first of all let me just write li3 of x, and then we know that its integral is li2 of 1 minus x. Yeah, and this is from 0 to 1 minus integral from 0 to 1. Now derivative of li3 of x is just li2 x by x. You should know this thing because we have already discussed this in our channel in previous videos as well. Yeah, this is a common thing. And now the other is li2 of 1 minus x dx. Yes, I should have used reading, sorry for that. Now at 1 li2 of 0 will be 0, at 0 li3 of 0 will be 0. So at both the values this expression goes to 0. So we just have zeta of 2, zeta of 3 minus integral from 0 to 1 of li2 x, li2 1 minus x by x dx. Yes, let me check if the progress we have made till now is correct or not. Let me check. Yeah, because it can sometimes get wrong. Yeah, so it's necessary to check. Yeah, it's correct. Now let's proceed forward. Okay, so now till now let us analyze the progress we have made. So basically till now for finding this expression we told that we will find the other expression, and now the other expression has reduced to this integral. So that means I have to solve this integral to solve the problem. Yeah, let me take this integral and let me paste it in other side. Let me paste it over here. Now let me do with other ink. Let's say green, and then paste the problem now. Let me paste the problem. Yeah, now let's solve this one now, this integral. So for solving this integral, we can first use the reflection formula, yeah, of full logarithms, that is Li2 of, I think this ink is not visible. Okay, Li2 of 1 minus x plus Li2 of x is, we know that this is equal to zeta of 2 minus ln x ln 1 minus x. We will use this reflection formula, and from here we get that Li2 of 1 minus x is basically Riemann zeta of 2 minus ln of x ln of 1 minus x minus Li2 of x. Yeah, so let's substitute this over there. And the reason is whenever there's this Li2 function and not Li2 1 minus x, it will be easier to solve. So that's the reason we are doing this. Li2 of x, yeah. Now that is Riemann zeta of 2 minus ln x ln of 1 minus x minus Li2x by x dx. Yeah. Whew, again there are three integrals. This is going a lot wild. Li2 x zeta of 2 by x dx. Yeah, and next minus integral from 0 to 1 Li2x ln of x ln of 1 minus x by x dx minus integral from 0 to 1 Li2 of x square by x dx. Okay, now we need to solve these three integrals. Yeah, okay, let's go ahead. Now for this one is easy because we will just use the property of polar logarithms, that the integral of Lip of x by x, this is just Lip plus 1, yeah, x. So using that we get this to be Li3 of x times zeta of 2, and this is from 0 to 1. So that's why I have Li3 of 1 zeta of 2 minus Li3 of 0 0, so this is also zeta of 3, so zeta of 3 zeta of 2. This one is solved easily. Now let's go to this one. How do we solve this? Okay, so what can we do is basically ln of 1 minus x by x, if here was minus sign, that would just be derivative of Li2 of x. Yeah, so again let's introduce by parts, but with this as u and the remaining expression as b. Yeah, that will make our thing simple, because the derivative of Li2 of x, oh, and also here's negative sign, so let's make this a positive sign, and let's play a minus sign over here, yeah, in front of ln, so that minus ln 1 minus x by x, this is just derivative of Li2 of x, so that will make things simpler. Yeah, so now this is now ln x as it is, and the remaining is just the derivative of Li2 of x. Yeah, so that's why it will just be Li2x whole square by 2, and this is from 0 to 1 minus, and next integral from 0 to 1 ln x derivative 1 by x, and its integral is Li2x whole square by 2 dx. Yeah, and then again we have a minus sign, integral from 0 to 1, let me do that later on, but not right now. Okay, dx. Now this one, at 1 this is 0, ln of 1 is 0, and at 0 this is 0, so that just becomes 0. And now this is minus 1 by 2, integral from 0 to 1 Li2x whole square by x dx. Okay, this is how this integral simplifies. And the last integral is same. Yeah, basically last integral is also let me write another ink. Last integral is also same. This is also minus integral from 0 to 1 Li2 of x whole square by x dx. Yes. So overall, if we, from these three integrals, what we get is zeta of 3, zeta of 2 minus 3 by 2 integral from 0 to 1 li2 of x whole square by x dx. Yes. So this is how these three integrals have simplified to. Now again, we need to find this expression over here to solve it. Yeah. The summary. Okay, to find this, we need to solve this sum. For this, we need to find this integral. Now for this integral, again, here's another integral, and let us see like how long will it go. When will we finally get the answer? Yeah, this is a long chain, but I hope that it's going good. Please don't be like stressed with the chain that we have come across, because eventually it's going to solve. I'm pretty sure about that. Now to solve this, we will basically use the sum of the li function, the sum definition of li function. Okay, so integral from 0 to 1 by x. There are two li2's function. Yeah, so one of them be sum from n equals to 1 to infinity x to the power n by n square. Again, there's another li function as well, sum from k equals to 1 to infinity x to the power k by k square. And again, last there is dx. Now let's change the integrals and sum. Sum from k equals to 1 to infinity, sum from n equals to 1 to infinity. This is x to the power n plus k minus 1, n plus k minus 1 by n k square dx. And integral from 0 to 1, not to forget that. Yes. And now next what's the next? Next is sum from k equals to 1 to infinity, sum from n equals to 1 to infinity. Now we have n k square, and from this we have 1 by n plus k. Yeah. Now if there are just n k's only independent of each other, not like the sum over here, we could have distributed each other sum and found out the answer. Yeah. But in this case, what to do? There's a way. The way is what we can do is we can basically group the n plus k, because the way you do it is this can be written down as a difference, as a partial fraction, 1 by n minus 1 by n plus k. And the partial fraction separates n. 1 by k also should be there. Yeah, because n plus k minus n, basically k comes in numerator, so k cancels out. Yeah, and by doing this, we know that if we had to sum this would actually be the harmonic number, and that's how it can simplify. Yeah, but right now again let us see and you will understand. So sum from k equals to 1 to infinity, sum from n equals to 1 to infinity. This is for now, this is just n square k cube minus this is k cube and n plus k. Yes. Now this can be simplified, but here again we can do the same thing. Yeah. Now this is sum from k equals to 1 to infinity, sum from n equals to 1 to infinity. This 1 by n square k cube can be simplified. Yeah. Now next, again, sum from k equals to 1 to infinity, sum from n equals to 1 to infinity. Now you can see that we can basically write this as 1 by n minus 1 by n plus k. Yeah, and also there should be a 1 by k over here. Yeah. Now this can be solved. Let me show you how. So basically now this is just Riemann zeta of 2, Riemann zeta of 3. Yeah, if we just assign these terms to each of their own sum. Over here also, this is sum from k equals to 1 to infinity, 1 by k to the power 4. And again, this is sum from n equals to 1 to infinity, 1 by n minus 1 by n plus k. Yeah, we know that this sum actually is just the kth harmonic number, h sub k. Yes, so if we know that, it is just hk. And now finally there comes a sum which we can easily find, and that's how it solves the integral. Now we know that we can easily find this sum, yeah, because this is just the classical Euler sum, which you already know. So again, let's go to another section. Let's make another section and another color. Yeah, and we know that we can easily solve this sum from k equals to 1 to infinity of hk by k to the power 4. Let's do the classical Euler formula, which we know that the classical Euler formula is 1 plus k, 1, if this is q, 1 plus q by 2 Riemann zeta of q plus 1 minus 1 by 2 sum from k equals to 1 to q minus 2 Riemann zeta of k plus 1 Riemann zeta of q minus k. This is the classical Euler sum. Yes? Yes. Okay, now this is the classical Euler sum, and using this we can find out the sum. That is basically 3 Riemann zeta of 5 minus 1 by 2 sum from k equals to 1 to q minus 2. Yeah, and then Riemann zeta of k plus 1 Riemann zeta of 4 minus k. So we get 3 times Riemann zeta of 5 minus 1 by 2. Since q is 4, 4 minus 2 is just 2. Yeah, and over here this is Riemann zeta of 3 Riemann zeta of 2 plus Riemann zeta of 2 Riemann when k is 2 Riemann zeta of 3, sorry, Riemann zeta of when k is 1, when k is 1, this is Riemann zeta of 2 times Riemann zeta of 3. In other case it is Riemann zeta of 3 times Riemann zeta of 2. So basically, yeah, you get the point. They are same basically. So since these are same, and so we can, if we divide by 2, we will just get one of them. 3 Riemann zeta of 5 minus Riemann zeta of 3 Riemann zeta of 2. So finally we have something that will solve the entire problem. Now we have this sum, so put it over here, and now we got step by step backward. If we put it over here, what do we get? 2 times Riemann zeta of 2 Riemann zeta of 3, yeah, minus 3 times Riemann zeta of 5. Is that it? Yeah, that is it. Now again, let me put it back to over here. If we put it back to over here, we get zeta of 3 zeta of 2 minus 3 by 2. Now this is 2 times zeta 2 zeta 3 minus 3 zeta 5. Yes, so that gives me zeta 3 zeta 2 minus 3 zeta 2 zeta 3 plus 9 by 2 plus 9 by 2 zeta 5. Is that it? Yeah, I think that it is. Okay, nice. Now this is 9 by 2 zeta 5 minus 3 zeta of 2 zeta of 3. Yes, basically 9 by 2 zeta 5 minus 3, not 3, sorry, this is 2. 1 minus 3 is minus 2. Yes, okay, 9 by 2 zeta 5 minus 2 zeta 2 zeta 3. Yes, good. Now again replace it back over here. Okay, so this is zeta of 2 zeta of 3 minus this expression over here, this expression over here is 9 by 2 zeta 5 minus 2 times zeta 2 zeta 3. Yes, this is the expression over here. So what do we get? Basically 3 times zeta 2 zeta 3 minus 9 by 2 zeta 5. Yes, okay, yes. Now finally we would have the answer now finally. So this the answer is basically zeta 3 zeta 2 plus zeta 5 minus the answer. Yeah, so our final answer basically written right with ink, light red black pen now. Zeta 2 zeta 3 plus zeta 5 minus this expression over here, which is 3 zeta 2 zeta 3 plus 9 by 2 zeta 5. Yes, so this is 11 by 2 zeta 5 minus 2 zeta 2 zeta 3. That is our final answer finally. Whew. Let us check if it's correct or not. Let us check, and like what would happen if it was incorrect. 11 zeta 5 by 2 minus 2 zeta 3. Oh, thank God the answer is correct. Yes, our efforts did bear some fruits, and this is the correct answer as we have got over here. And now let us talk about the flow. The flow is also too long. It basically took me 1 page, 2 pages, 1 2 3 4 5. It took 5 pages. Okay, now let's talk about the flow. So first of all, to find this expression, we were basically finding the other expression, because that would make the ln x simpler. Yeah, and the other expression again involved a nice polylogarithmic integrals, dilogarithmic integrals, and for here, because this is basically from the integral representation of the Euler sum with r equals to 1. Yeah, again now this is from the reflection formula of Euler logarithms, and then we got some integrals that were needed to be solved, and now we ended up with this integral. Now for that again we used the sum formula of Euler logarithm, and that finally gave us this simpler sum, which could be solved using classical Euler formula, which is this over here. And from classical Euler formula we finally got the values. So it all ended up to Euler. Thanks to Euler for giving us the solution. And then we got the answer, and substitute back, and you get the answer. So that was it. Hope you enjoyed the video. Thanks for watching, and look forward to seeing in the upcoming videos too. Do enjoy such contents.